Welcome back to the next Keto Naturopath. I'm Dr. Carl Goldkamp. Today we're going to continue going into the study that we looked at that talked about reversing epigenetic aging, which is actual aging, using no more than food and more or less just one supplement, and it's just some phytonutrients. Could they get such good results? They did. For the majority of the people, they got great results, but yet one didn't. So let's look into why the difference. What could we boil this down to? All right. So how to make epigenetic reverse aging work for you in 4 parts. We're going to do 2 today and 2 in another video. Okay, this is the study we're looking at, potential reversal of epigenetic age using a diet and lifestyle intervention. But done back last April 15th, 2021, tax day. Okay, so in order to look more deeply, what we got to do is we want to understand the results to the study and why everyone didn't benefit, become younger. How can you use these results to increase your own health span? Remember, health span is the number of years we're healthy. So take it out to 100. We talked about in the United States that the average health span ends at 63. The average lifespan ends at 79. So that's 16 years of living pretty miserably. I'm not just talking about those 16 years. I'm talking about reversing the rates of chronic disease. As you know, in former videos, that the rate of chronic disease in the United States is 60% of all ages, whereas in 1935 it was under 7%. Why is that? It's hard to point to just one factor, but we can say a decline in nutrition for the majority of us. We can say it's the increase of toxins in our environment, and you can go from there. But we're going to boil that down to methylation, epigenetic methylation. All right, so nugget number 1, understanding the results of the study. Why didn't everyone benefit and become younger? Why the difference in the results from person to person? Isn't this for anybody? For everybody? Why did some actually get worse on the program? Let's look at their data. Okay, so what was measured? What they did is they got an expensive test, in essence, in which they got the saliva and did all this appropriately, sent it off to Yale. Yale sent it to McGill, and McGill sent it back to the head of the study to get the data interpreted. Well, not everybody can do this, and certainly your doctor is not going to be able to do this for you. However, there is a company based on the same testing that actually has come out a couple months ago that you now can do it individually. It will cost, like all labs will cost. We'll get into that. And the second, they did some basic blood work. They looked at triglycerides, they looked at total cholesterol, they looked at folate in the blood, and let's look at it. So they said triglycerides came down about 25%. So triglycerides, they said, was on the average of 112, came down to 89. The ideal number for triglycerides around 70. What is triglycerides? Triglycerides, if you will, fats, is all about carbohydrates. So whether you're a sugar consumer, whether you're a potato consumer, potato chips, cereal, crackers, Twinkies, whatever it is, processed foods, if you will, you're going to have higher triglycerides. And I've seen it up to even over 1,000. That's extremely high. So this audience of 112 to 89 is really not terrible at all by any means. Elevated folate. Now, why is it good to increase folate? Well, it's not necessarily always good. If there was a deficiency, it's good to increase it. But they were all given, as you will see, a folate-rich diet, and hence it increased 15%. Total cholesterol, it's a useless test, actually, in my view, to take. But they did to keep the conversation going. So they said total cholesterol decreased about 22%. And LDL went down a little bit as well. Other than that, they said on the other tests they did, such as glucose and hemoglobin 1AC, which is what diabetics are required to have, and it's pretty much a redundant test to glucose levels, that they said that was normal. We'll find out. I don't have any data on that. And they did 4 tests here: methionine, homocysteine, SAM, and SA. S-adenyl methionine, S-adenyl homocysteine. So really, 2 tests and 2 variations of those 2 tests. We'll look at those and why those are important. Spoiler alert, this is what they call the poor man's methylation test, is to get this ratio right here. Okay, so this is what was required of these particular men from ages late 40s to 72. Each week, they had to have 9 ounces of liver. They had to have 6 ounces of animal protein per day, grass-fed, pastured, organic, hormone, antibiotic-free. The real deal. 7 to 10 eggs, omega-3 enriched preferred. That's a big deal. As we looked into former videos on this research, on this study, we showed the value of omega-3 enriched eggs really changes the omega-6-3 ratio significantly. And we looked at that in Chronometer. Okay, here's the veggies they had to have. Quickly, 2 cups of dark green leafy vegetables, 2 cups of cruciferous to support the glutathione, what they call transsulfuration pathway, colorful vegetables, that's your carotenoids, 2 beets, pumpkin seeds, sunflower seeds, and here's what they call methylation adaptogens in their supplements. And we'll get to that in a second. Green tea, oolong tea. You notice there's no coffee. Okay, methylation clocks, which is the other thing that they measured. This is the thing that they had to get the saliva, send it to Yale to McGill, and get the results back. It had to be done specially, all on dry ice, et cetera, et cetera. Methylation clocks are based on a systemic methylation changes with age. Systemic, the whole body. Methylation changes with age. They call this a DNA M clock. So it's DNA methylation age clock. Shows that 60% of these methylation sites that they're looking for that are technically called, I'm sorry, this is going to be technical just for this slide, CpG sites. 60% become unmethylated. They lose their methylation with age. 40% gain methylation when they weren't supposed to have been methylated. So they become turned on if they lost their methylation. They become turned off when they get methylated. That's a problem. So what this means is 60% of the genes are not methylated, it should be. 40% are methylated, it should not be. Methylated genes are turned off. Unmethylated genes are turned on. They're allowed to function. Why would you care about this back and forth? Because not all genes have to be on at the same time. If I took any cell in my body, it contains the same DNA as my whole body. So why is a heart and not a big toe? Why is an eyeball and not a stomach? That's because certain genes are turned on and certain genes are turned off. So the more careful, the more critical your body is of saying, these are the appropriate genes to be methylated, turned off. These are the appropriate genes to be turned on. That's the process you need. Not all methylation and not just demethylating, right? Who needs to be methylated is the key to keep that balance between methylated and unmethylated. Okay, these are the results. So these are all the guys that got younger. One guy actually got significantly older, and here's how you read this. This beige line in the middle means this. I'll insert myself here. Let's say I'm 50 years old at the beginning of the test, and at the end of the test, I'll still 50 years old. Then I would simply be a dot on that line, like there were. There were a lot of dots near or on that line. They didn't get any change one way or the other. One guy, so he had to be about 48. One guy went from 48 to about 58. Bummer. He got older. Everybody else got younger. So if you're on this side, you got younger. If on that side, they got older. So they weren't successful here. They were successful here. Here's what they said. Said all in all, on the average, everybody got about 2 years younger of the 18 final that were analyzed in the end. 8 scored age reduction, 9 were unchanged, and 1 increased in methylation age. 1 increased in methylation age. Okay, so this study targeted the idea of healthy methylation pattern. What is a healthy methylation pattern? A healthy methylation pattern is exactly this. It's the ability to create the necessary balance between methylating, turning off the genes that need to be turned off, right? We're turning off all my eyeball genes in my big toe. I don't need an eyeball there. And we're turning off all my big toe genes in my eyeball. A little facetious there, right? And we also have to have the ability to unmethylate genes that were unmethylated. Their time has come to be now made functional. So it's that balance. See the balance, not just one way or the other. So we're either turning genes on or off appropriately in the appropriate place. Okay, demethylating nutrients. This is a new concept. Haven't heard that before, I'm sure. And so this is what they put together in one of the prescribed supplements, such as vitamin A and C. And these little numbers here are footnotes that you can look up in the study that I will put in the description of this video. So you can go at it. And specific plant polyphenols, such as curcumin, EGCG was called Epigenetic catechin, and is what you get from green tea. These are known to demethylate. They demethylate. These are the demethylators. And so they support demethylation of genes, right? Taking the methylated group off and activating that gene. They're going to be activating genes. Food source methyl donor nutrient in high quantities came from the diet. That whole diet that I just outlined, the liver and the eggs, the egg yolks, and those veggies gave them plenty of methyl donors. So, as evidenced by the younger DNA MH test, that is, most improved methylation patterns is what they achieved, right? The majority did improve, that average of 2 years. It suggests that these compounds collectively assist in elevating methylation and demethylation enzymatic support. So they're saying this is actually a pretty neat thing. This balance, this gave us the balance. Because for decades we've been hearing about, oh, methyl donors. They need to have methyl donors. I mean, that was way back from year 2000, even in med school. Hey, give them methyl donors. No, that's just supporting one side. You can overmethylate people. So overmethylating, undermethylating is a problem. So in addition to the combination of polyphenols, rather than use single phytonutrients, so they didn't just say, hey, take this supplement. They said, let's just do it, in essence, with food. Here's a powdered drink, in essence, have a scoop of per day, and this is what it's going to have in balance with your diet. Pretty clever. They wanted to show if it was possible to create a healthier methylation pattern through whole foods and phytonutrients in a supplement. That's pretty radical thinking. Using food as your medicine. I know it goes back 400 or 500 years BC to Hippocrates, but it's been laughed at for the last 70 years, for the most part. That means that to demethylate genes that were methylated, right, to demethylate the hypermethylated genes, turning them on, and yet they've been turned off, and to not methylate and to unmethylate genes that were methylated. That's profound. So if you were to say this, hey, we're just going to use food and some phytonutrients to kind of achieve a methylation balance, that would have been a joke. So it had to be supported by a naturopathic school, or Epigenetics in particular. Consequences of being hypomethylated or hypermethylated. It's a real thing. All right, so when you're hypomethylated, right, not enough genes are turned off. You're under, hypo, think of like hypothyroid. So hypomethylated means that genes are on that shouldn't be. So consequently, things are growing and processes are happening that shouldn't be. Cancers fall into this. And they find with various cancers and tumors, whether they're benign or malignant, is that when they look at the genes of the tumor, they're all unmethylated. Everything's just going crazy. It's all on. Okay, when things are methylated, they're not allowed to replicate. They're just turned off. And so you get diseases either way. And what they find for this imbalance, the imbalance between methylation and unmethylation, are all these diseases, Fragile X, Rett syndrome, on to the next page. Well, coming up. So methylated and unmethylated, this is what it looks like. It's this little island before the gene, the little island before the gene. These are methylated, so this gene is turned off. These are not methylated, so the gene is allowed to express itself, to do what it's supposed to do. So symptoms and traits of undermethylation, symptoms and traits of not having enough genes turned off, that are supposed to be off. Chronic depression, history of perfectionism, seasonal allergies, history of oppositional defense. They have strong opinions. You know, your opinion is always wrong. They're always right. High libido. They have adverse reaction to benzodiazepines and folic acid, taking a supplement. They have a good response to SSRIs and antihistamines. They have sparse body hair, suicidal tendencies, addictiveness, phobias, obsessive compulsive tendencies, ritualistic behaviors. They got to be out of bed at a particular time. When they get up, they got to be to bed by a specific time. They have to be boom, boom, boom. It's good to be punctual, but they have that all over their life. And not just in terms of time, but other things. They might always have to wash their hands a certain way, whatever. or comb their hair a certain way. Self-motivated during school years, history of competitiveness in sports, strong-willed, calm demeanor but high inner tension, family history of high accomplishment, frequent headaches, slenderness, dietary inflexibility, terse speech. I'm in that group, by the way. Symptoms and traits of overmethylation. They have too many genes that are turned off that should be on. What do they look like? Kind of the opposite of what I just read you, but here we go. High anxiety, panic, hyperactivity, rapid speech, low libido, religiosity, right? God told me to do this, and I'm going to stick with it. Tendency to be overweight, nervous, leg pacing, adverse reactions to SSRIs and S-medenylethiamine, SAMI, improvement with benzodiazepines, food chemical sensitivity, artistic or musical ability, copper overload, estrogen and antihistamine intolerance. So antihistamine intolerance, and the other one was made better with antihistamines. Okay, absence of seasonal allergies, dry eyes and mouth, low motivation, depression, self-mutilation, sleep disorder, tinnitus, and hirsutism. So I have to tell you about this antihistamine. So why is antihistamine intolerance? So these are about being overmethylated. They have too much methylation, and they have an antihistamine intolerance. So what happens is that with antihistamines, we used to consider it a side effect, as antihistamines would deplete folate. They would deplete folate, and we thought, oh, it's a side effect, so you have to give folate. But when you are overmethylated, you don't have enough methylated folate, and so by decreasing your folate, actually you need methylated folate. By decreasing that, you improve the situation. All right, short list of conditions associated with hyper and hypomethylation. These are just from a previous slides: Fragile X, Rett syndrome, autism, the entire spectrum, schizophrenia, dementia, suicidal risk, Prader-Willi syndrome, Angelman syndrome, Beckwith, Weiderman syndrome, and many more. What I'm trying to show you, it's something that's gotten worse. It correlates with a lot of other things going on in the world, but we'll keep it pretty specific here. This is about methylation. We're getting right into the blood work. We're getting right into data-driven decision-making. We're looking at the data of a test. We're not just, take a magnesium supplement and life will be good. No, it's a little bit deeper. It's a little more focused, a little more educated, but not outside of what you can do for yourself. That's the point of this whole little video. Okay, so let's look at autism. 1970, 1 in 10,000. 25 years later, 1 in 1,000. That's a 10-time increase. From 95, 1 in 1,000, to now in 2020, call that this year, but we're 2021, 1 in 54. And that was just since 2000. So they measured from here, 1 in 150. That's 178% increase. So it's just obviously gone nuts. All right, part 2, MTHFR and epigenetic reverse aging. Why do I even bring that up, this whole thing? Well, I corresponded with the author of this particular study, one of the lead authors, Dr. Cara Fitzgerald, corresponded with her via email, and I asked her some questions, and she was nice enough to get back. So what they did labs and MTHFR. So what I asked her was, did you consider doing an abbreviated genomic analysis, something like Stratagene or Opus 23, a similar analysis? And she said, her answer was, we ran a basic SNP panel, that's what these are, which may be published later on. But there is some suggestion that, here we go, there is some suggestion that MTHFR SNPs of any type respond very well to the program. So here's the take home. MTHFR SNPs of any type respond very well to the program. So I pose the question now to you, to me. Why might this be, and what does this mean for you? So why might this be that MTHFR SNPs of any type respond very well to the program, and what does this mean for you? So most of the people, right, most of these guys responded well, some didn't. We've seen this before. A simple abnormality in the methylation pathway can lead to a wide range of conditions. So now we're talking about methylation pathway abnormalities we'll get into. So these are all the conditions associated with methylation pathway abnormalities. Cardiovascular disease, neurotransmitter imbalances. So think of addiction, dopamine deficiency, serotonin deficiency, cancer, diabetes, abnormal immune function, chronic fatigue syndrome, multiple sclerosis, cognitive dysfunction in patients with dementia, neurological and psychiatric disorders, Alzheimer's disease, Down syndrome, autism, neural tube defects for sure, and chronic inflammation. So SNPs, single nuclear polymorphisms, and methylation. This is how we look at it. So we go and we get, this happens to be Strategene from what they used to do a couple of years ago. And so I use this on previous videos as well. This is an anonymous male, kept it to the male, and saying, well, he had he had the worst mutation you could have for MTHFR. He also had the worst mutation you could have for MTHFR. These are, and you can see where these are in a second. And CBS, which has to do with glutathione production. So he was pretty compromised. His family history was about diabetes and addiction. Here's another way of looking at it. Same company, Strategene. They've become really expanded what they test, and so they consequently changed how they present it. All the purple are things that are slowed down mutation that they have, and all the red ones are the ones that go faster. So we look at S-medenylethianine, pretty slow in this person's ability to produce SAM, or SAMe, pretty slow in the ability to produce folate, and doing okay with glutathione. So for instance, that's how you can look at these things. All right, here we're going to just look at what I used to call traffic circles. This is your neurotransmitter synthesis, your folate acid cycle, your methylation cycle. It's an oversimplification, but it's to give the concept of interlinking systems, interlinking cycles. But MTHFR is here, MTHFR, think of the guy I just showed you, blocked, blocked, and partially blocked. And here's, these two are the same view, but this one now shows cofactors, B12, B2, folic acid, vitamin B6, and there's SAMe. So why would you care? Well, if you don't have the cofactors, these enzymes are not going to work very well. And if you already have a problem, already have a compromised function for that enzyme, and you're not getting the cofactors, you are really up a tree. You're going to have a potentially serious problem. And that's how this is. And so you look for these things that need these cofactors, and it's not exactly plugging in, the missing buttons on the shirt kind of thing. It's looking at the bigger picture and how they need, do they need methyl donors? Do they need just the opposite? But this is where you look. This is the methylation pathway. Again, the methylation pathway. This is your methylation cycle. This is your folate acid cycle. Why would you care? This is what they did in the blood work. Methionine, homocysteine, SAM, and SA, right? And this shows if they're not getting enough SAM, you can't methylate, turn off those genes. And so when we get older, or even those who have genetic problems, can't methylate. So in other words, a lot of their genes are left running. They're on functioning where they shouldn't be functioning. And so this is what they tested. This little loop here, this ratio, again, is the poor man's methylation test. In other words, it saves you a trip to Yale and McGill and so on and so forth. But we'll take a look at that. Here's another way of looking at the same thing, just structured a little bit differently. There's the MTHFR. Remember, she said anybody who had a problem here will benefit very much from the program. Why is that? Well, they would probably need another level of nutrition to be able to help get that balance between methylating, so they need methyl donors, and they need demethylating agents, potentially. There's the SAM-SA as a lab that they measured, and there's methionine and homocysteine. So if SAM is not working properly, it can't methylate those groups, can't turn off the genes. Glutathione is down here, so anybody who has any of these problems here that we've looked at, and there's other slides, would also have a problem with glutathione, and therefore would also have a problem with inflammation. DNA methylation testing, usually done in white blood cells called lymphocytes. And here's the plasma biomarkers, such as SAM-SA ratio, have been shown to correlate with changes in DNA methylation, the poor man's. So here's the CPG islands that get methylated, right? Here's another way of looking at these islands before the gene that turn on the gene or turn off the gene. If these are methylated, that gene is turned off. If they're not methylated, the gene can function. Okay, so here's the last slide, and this is basically saying this is what they're looking at. Do we have a functioning methylation pathway. Can we methylate? Can we demethylate? And this is, can we achieve a healthy methylation pattern? We're going to pick it up from here next time to go into health span and to look at a little of the history of epigenetics and to show you why this is important and just some basic things you can do either by blood work, either by test, or for yourself. Till then, bye-bye.